let me thank the Physical Oceanography Lab for the nachos and snacks. It's my pleasure today to introduce Dr. Maya Reimi, paleoclimatologist and isotope geochemist. She did her PhD at Texas A&M, where she used isotopes to understand changes in dust provenance and ocean water masses in the Central Pacific. Now she's doing her postdoc at UCSC, where she's working with Dr. Christina Ravella, who's one of Ivano's close collaborators. And her current research centers around understanding changes in the Indo-Pacific warm pool. So let's give a big hand to Maya.
Thank you. Thank you so much for inviting me and for the introduction. I'm really happy to be here. And we're going to talk about tectonic shifts and Pliocene climate. So I know it's a little different from what a lot of you guys do, and I'm going to try to bring all the concepts at a good pace. And if you stick with me, we'll make it through the end. So first and foremost, I would like to thank my team. The research that I'm going to present today is actually the result of a long collaboration between former members of the Ravella lab who generated all of these records. And I just kind of swooped in at the end to bring it all together and write it up, which is a perfect situation if you ask me. But want to recognize that this is the work of a lot of people, and it took a lot of time. So this presentation is in two parts. The first part is about why do we even bother to study climate in the Pliocene? And then the second part is what did I do, or what did they do, but then I came in and swooped in it. And then the data and the interpretations, and what does that mean for the Indo-Pacific warm pool? So first, why should we construct records of past climate? This sounds a little cheesy, but like a good historian, understanding the past is the key to predicting the future, to understanding our future. Obviously, when we talk about geologic climate, there are things that happen in geologic time that are not going to repeat themselves once we look into future climate change. Tectonic changes, orbital parameter changes that are not going to be there in the next couple centuries. But understanding how much of past climate change is due to geologic events is going to give us a lot of information about the mechanisms of climate change and give modelers a lot of information for how to predict climate. So this is our journey through the past. We have all of geologic history. And here in this little orange slice is where we're going to focus our time, which is the Pliocene Pleistocene. And then right here towards the edge is all of human civilization. So this plot is a little confusing because we have changes in temperature records through time, but as we are approaching modern time over here, our records are getting better and better in resolution, right? So there's these shifts in time, in temporal resolution. This actually matches what our proxies do, which is as we get closer to modern times, our proxy records have better and better resolution. But here we're going to focus on the Mid-Pliocene and the Pliocene-Pleistocene transition, this big chunk of time. And there's a couple of things we should know about the Pliocene. First, we have our pre-industrial baseline, and we can see that the Pliocene is the most recent event where temperatures were much warmer than they are today. This is obviously a much faster transition, but a period of time where it's much warmer than it is today. And then we also know that during the Pliocene, Northern Hemisphere ice sheets were not fully developed. At the beginning of the Pliocene, you had sporadic Northern Hemisphere ice sheets, and at some point in the Pliocene, and the actual dating and the actual causes for this are still to be well understood, the Northern Hemisphere ice sheets became well developed. So now you have permanent ice in the North Pole for as long as it lasts. And then we have our future predictions of climate are these ranges here. And where we actually end up falling will depend on the choices we make, right? Are we going to end up in the Eocene-style warming, or are we going to experience a much milder warming? That's going to depend on modern choices. But the Mid-Pliocene is actually an analog for a big section of these predictions. And here's the time that I'm going to be talking about today. So another thing that we know about the Pliocene, and here we have a record of carbon dioxide in different carbon dioxide proxies and time, and now time is moving in the paleoclimate way, which is with the most recent things here, and then time going up that direction. And we have a record of different carbon dioxide reconstructions based on different proxies, some from organic geochemical tracers, and some of them are from boron isotope records that say that the Pliocene was also the Mid-Pliocene in particular also had higher carbon dioxides than this post-industrial mound. Here we have the 400 ppm carbon dioxide threshold. And we also know that in the Pliocene, here's what the sea surface temperature anomaly looked like. And most of the increased temperatures in the Pliocene were focused at the polar regions, and the subtropics and the polar regions. So a quick summary of things that we know about the Pliocene warm period and some things that we don't know. So I mentioned that temperatures were warmer than modern temperatures, about 3 degrees. We have higher CO2, about 30% higher than pre-industrial. The northern hemisphere ice sheets were sporadic. I haven't mentioned that the Antarctic's ice sheets were smaller. Sea level was about 10 to 20 meters higher. And we had enhanced meridional overturning circulation. And things that we definitely don't know about the Pliocene is, why did it end? Like, why did it begin cooling? And was this cooling a response to a low altitude or a high latitude event? So we're mostly going to focus on that, on was the cooling the response to a low latitude or high latitude event. But first, we have to take a quick detour to talk about methods. So this work all focuses on foraminifera proxies. The first one is a proxy for temperature, which is foraminifera magnesium calcium. And the one thing that I didn't really cover is that these are planktonic foraminifera. They're growing in the seawater, and depending on the species of foraminifera, they have different depth habitats. But I will also talk later about benthic foraminifera that are growing at the sediment-water interface. So foraminifera magnesium calcium, the calcium ratio that is incorporated into the foraminifera shell depends on the magnesium-calcium ratio of the water that it grows in, but most importantly, the temperature. So when the temperature of the water is higher, foraminifera incorporates more magnesium relative to calcium. And when the temperature is lower, it incorporates less magnesium relative to calcium. And here we're going to mostly talk about Globoralia tumida, which is a thermocline-dwelling foraminifera species. So we're trying to reconstruct thermocline temperatures. And one of the things that we need to know about having tumida as our proxy is that when you have a tumida temperature reconstruction, you don't necessarily know if the thermocline is deeper or if the thermocline is colder or shallower. You know, you don't necessarily have a good idea of the depth of the thermocline relative to the temperature of the thermocline unless you have another way of looking, right? The magnesium calcium itself is not going to give you the answer. So we have, and importantly, there's biogenic effects. So the foraminifera, who are a species of the zooplankton, have a preference for taking magnesium relative to calcium. So you also have to calibrate each species of foraminifera that you're using and have a good idea of what the temperature to magnesium calcium ratio is for that species and hope that it doesn't change over time. And then we have our oxygen isotope system. So this is going to be a very quick overview of oxygen isotopes. And then you have to trust me, and I'll carry you with me through the rest of the talk. So there's a couple of things that are important. One is that you have the oxygen isotope ratio of the water, and you have the oxygen isotope ratio that gets incorporated into the foraminifera shell, which are slightly different things, right? So for the water system, it's mostly about a balance between ice, precipitation, and evaporation. Ice tends to have lighter oxygen isotopes than water. So if you are creating a lot of ice and that ice is being trapped in the continents, your water is going to be more enriched. So it's going to be heavier water, right? You took all the light stuff away and you put it in ice and you trap the ice in continents. And similarly with evaporation and precipitation, if you're evaporating a lot of this light water and moving it away and precipitating it somewhere else, your local water mass is going to be more enriched. And then for the foraminifera, when you have warmer waters, you have lower oxygen isotope values. So you have, So when you have this beautiful, very common Lisecki and Reimi scale, and now we have time, once again, moving this direction in thousands of years. So this is a 5 million year record or a 5,000 year record. We have our lower oxygen, so they reverse the scale just to be extra helpful. You have our lower ratios over here and our higher ratios down there. So with lower ratios, you have warmer temperatures or less ice. And with higher ratios, you have colder temperatures or more ice or more ice. So here you have the Pliocene period, which is warmer and it has less ice. As we talked about, the northern hemisphere ice sheets had not fully developed. And here we have our Pleistocene, where we are developing northern hemisphere ice sheets, and also critically at some point in the mid-Pleistocene, we transition from a global climate dominated by a 41,000 year cycle to a global climate that is dominated by a 100,000 year cycle in glacial interglacial timing. And I'm not really going to talk about that transition. It is another aspect of the Pliocene and the Pleistocene that is very puzzling. But I just wanted you to know what the oxygen isotopes in benthic foraminifera. So the benthic foraminifera are more like a baseline for global change. And then we have our carbon system, which is actually the complicated one. The other one was simple, and then this one is the really complicated one, where the carbon isotope reservoir of water depends on a lot of things. It depends on how much vegetation there is on Earth and the type of vegetation. It depends on the amount of weathering. It depends on the amount of carbon dioxide in the atmosphere. So there's all of these competing things that are going to determine what the carbon isotopes of water, and therefore the carbon isotopes of foraminifera shells, are going to be. And this is the reason why there are a lot of unpublished carbon isotopes in foraminifera, because people generate them, and then it's really hard to interpret, so they quit. And I will attempt to interpret the carbon isotope record that we generated, because I was told that there are no isotope experts here. I will do it confidently. So carbon isotopes also vary in the water column. So these are two species of planktonic foraminifera, one that grows a little shallower and one that grows a little deeper, and deuterite is more of an equivalent of what Geotumida does. And you have the carbon isotope records are changing with depth. So that's really important when we are trying to argue that the foraminifera that we saw through time did not change its depth habitat if we know what the carbon isotope was. So a quick summary of what we learned so far about isotope systems. In benthic foraminifera, the oxygen isotopes become more negative, or it decrease where it's warmer and when there's less ice volume, and they increase when it's colder and when there's more ice volume. And in planktonic foraminifera, it's the same. They're affected by temperature and ice volume, but they're also affected by local precipitation. Benthic foraminifera are not really affected by local precipitation. They're recording a global signal. And in carbon, it's very similar. The benthic foraminifera are recording a global signal. So older waters have more negative carbon isotope ratios, and also they're also reflecting the amount of continental weathering, although also any changes in composition in the terrestrial biosphere. And then planktonic foraminifera, and this is why it gets so complicated, is that they can go down due to decreases in productivity, but also increases in local productivity due to changes in upwelling. So that becomes really hard to interpret carbon isotopes relative to productivity. But a thing that's important to know is that they're also reflecting the carbon isotope of the water that was flowing through them. So every water has a relatively unique carbon isotope signature. So that's what's really important for this talk. So let's go back to the question that we had. So was cooling a response to a low latitude or to a high latitude process? And we're going to focus on the low latitude mostly. So here is a map of thermohaline circulation. And we are going to center the rest of the talk right here, where we have this shallow, warm current that's flowing from the Pacific into the Indian Ocean through the Indonesian Throughflow. So an Indo-Pacific warm pool is this defined as the area of the ocean surface that is greater in temperature than 28 degrees Celsius. It's right here in the Indo-Pacific. And we have two sites in the Indo-Pacific warm pool that are going to get started, one in the Indian Ocean and one in the Pacific. And the key about the Indo-Pacific warm pool is that it's the largest mass of very warm temperatures in the ocean. And changes in the Indo-Pacific warm pool are going to affect atmospheric circulation and ocean circulations and global climate. So if we're trying to find a candidate for generating big changes in global climate, the Indo-Pacific warm pool is a good place to start. And here we have a more detailed map of surface currents that are going through the Indonesian throughflow. And we can see that because the Indonesian throughflow is so restricted, it gets really messy once you get here, right? So you have these very warm matters, they travel, and then they get to the Indian Ocean. So it's not a very direct path, which complicates studying it. But the entire reason why I said we were going to talk about tectonic shifts is that there was a model by Kane and Molnar in 2001 that said that the northward trajectory of Australia and Papua New Guinea, so they used to be further south in the Pliocene, and then they started moving northward where they are today, that this movement made the Indonesian throughflow smaller, right? I mean, it makes sense. It used to be a little bigger, and now it's smaller, it's shallower, and it's really affecting what kinds of waters make it through it. But that it actually made it so that the southern Pacific Ocean was warmer in the thermocline depths, and that the thermocline in the Indian Ocean was cooler, and that cooling of the Indian Ocean in turn cooled and dried Africa. So this is a big hypothesis, saying that tectonic shifts and the closing of these sea weights are then transferring themselves through global climate. And here we have a research by Cross et al. That they suggested that they had actually found this, that they had found evidence that the thermocline became cooler, and not only the thermocline became cooler right here towards the end of the Indonesian throughflow, but that it definitely cooled Southeast Africa, and then they hypothesized that that was one of the reasons why Northern Hemisphere ice sheets became well developed. And here is some of their evidence. So we have now they're only looking at the Pliocene from 2 million to 6 million years, and we have a sea surface temperature record in different scales. It's important to know that 806 is warmer than 214, so the West Pacific is warmer than this Southeast Indian site, but they're in different scales. And then we have our oxygen isotopes as suggesting that there was a decrease in freshness, right? So it became saltier in this very critical time period between 3.5 and 3 million years ago. And once they reconstructed temperature, so we have the same 2.5 to 6 million year record here, and we have reconstructed temperatures, they saw a really big shift in G. cruciformis, which is a thermocline dwelling species. It's a really big shift in thermocline temperatures. And they said, we see that the temperatures really decrease. That must be caused by the Indonesian throughflow. We got the big global climate cooling hypothesis, right? And it's really complicated. So all of these things have to happen at the same time. But the idea is that you have warming in the West Pacific, cooling in the Indian Ocean. Then you have warming in the South Atlantic, you weaken AMOC, you lead to sea surface temperature cooling. It's so cool in the North Atlantic, and now you have ice everywhere. And the Pliocene cooling begins. It's a really bold hypothesis, right? Saying that you close one sea gate, and then you just trigger all these changes through climate. And we said, okay, how will that affect the Indo-Pacific warm pool, right? So all of these things were happening in the southern Indian Ocean in this site that they have right here. So we said, okay, if this is this really big global climate changes, like how are they affecting the Indo-Pacific warm pool? And we looked at this record from the Indian Ocean site, and we compared it to a West Pacific record. And here's the more detail of the Indo-Pacific throughflow. So we have a section where we have depth in the y-axis, and longitude in the x-axis, and then temperatures are like z-axis, right? So the Indo-Pacific throughflow is really restricted. There's not a lot of space to have a really cold thermocline water coming through the Indo-Pacific warm pool, right? So that this cooling that you are then transferring to the southern Indian Ocean has to be coming from somewhere in the Pacific, right? Like, you have to cool it quite a bit. So we said, okay, let's see. So we created this record, and here's our northern Indian side in red and our West Pacific side in blue. This is a 0 to 5 million year old record. We have our trusting Elarostock benthic isotope stack just as a reference for what's global climate like. We have the Pliocene, we have the Pleistocene. We can see right away that in the Pliocene, the northern Indian Ocean is fresher, so you have like lower oxygen isotope values than the West Pacific. And then at some point in the Pliocene, they sort of come together. But we see that in temperatures, the West Pacific is warmer than the Indian Ocean side, and we expect this. And then the northern Indian Ocean side seems to cool less slowly than the West Pacific side. So in the hypothesis that I just presented, you will have warming in the West Pacific and then cooling in the Indian Ocean. But here, we actually see cooling in the West Pacific, and then also cooling in the northern Indian Ocean, but like maybe like slightly slower cooling, which is just not as pretty or flashy, right? It's just like, it's a little bit less cold, as I'm saying confidently. So here we have our thermocline depths, and we said, okay, well, is this a global signal? Like, is this just a tropical signal? Is it a tropical cooling? Does it have, like, what's happening in the rest of the tropics? And maybe we can isolate the effect of the Indonesian throughflow if we look a little bit further, right? So we added data from the site in the East Pacific, 847, and this is the 849 data is mostly just a benthic carbon record. We said, okay, what does it look like if you add the East Pacific? So you add like a very far away record that has nothing to do with the Indonesian throughflow. What do these records look like? So the East Pacific is colder. We have here our temperature record. Once again, we're staying in the 0 to 5 million year range. We have our oxygen record, our temperature record, and a carbon record. We see that the East Pacific is colder than the other two records, and we expect this because the East Pacific is at the edge of the Pacific cold tongue. But we also see the same sort of like general cooling trend, right? I mean, I know that this is scattery and messy, but you have this general cooling trend that you're seeing in the West Pacific, and you're also seeing in the North Indian Ocean. And then critically, our carbon isotopes are increasing with time, very gently, but increasing with time, which is not what you would expect if the depth habitat of Tumida was decreasing, right? Like, if that wasn't a real change in thermocline temperature, if it was just a change in the habitat of this species, you will expect the carbon isotopes to go down as temperatures decrease. But you see either no change or maybe slightly increase in carbon isotopes, which is good news for us because it says, like, okay, we have a temperature effect that is separate from whatever else is happening with the thermocline. And here we can say, okay, let's isolate that West Pacific site, and then look at the differences. In this case, actually, the west to east differences between our site at the northern Indian Ocean and our site in the East Pacific, and our site in the West Pacific, and our site in the East Pacific. And we see first, like, there doesn't seem to be a really like step-like cooling between 3 and 4, like of one side relative to the other. If anything, we just have the same thing that we observed before when one side is cooling, and then the other side is just cooling a little slower. But the sites are coming together, which is not what you would expect if this hypothesis was right. You wouldn't expect the temperatures of the sites to converge. You will expect them to diverge. So we said, okay, that's interesting. let's look at the carbons and let's say, okay, I had said earlier that the carbon isotopes were distinct and that they didn't suggest a change in the depth habitat of 2 meter. But in order for me to actually say that more confidently, I have to subtract any global effects in carbon. So here we have our same 0 to 5 record, and this time we're looking at our Atlantic foraminiferous species, the 2 meter, and our benthic foraminiferous record. This is multiple species of benthic foraminifera. But we can see that it doesn't seem like they're really following a global trend. The global trend is dominated by this W pattern of eccentricity cycles. And even though we see some changes that are matching that, it doesn't seem to be the dominant trend. But we can actually subtract the benthic foraminifera and then look to see if that was a dominant pattern. So without the benthic carbon signal, the records still show a slight increase through time. There are some shorter length variations that are probably an amplification of that global signal. But you don't really see, you don't see a decrease in the carbon through time. And you see a lot more variation on carbon through time, which is probably related to a decoupling of the nucleocline and the thermocline, or, I don't know. But it's definitely not just a linear relationship between decrease in temperatures and decrease in depths. So that's good for us. It means that we can trust our 2 meter record a little bit more. And it also it just doesn't suggest that the Indian Ocean side becomes more like the West Pacific with time, right? There are some periods, specifically right here after the Mid-Pleistocene transition, where maybe that is the case. So maybe that is another place to look at these big changes in global climate. But we're talking about this slide between 3 and 4, and there, you don't have a lot of evidence that the East Indian Ocean is becoming more like the West Pacific. So let's bring it all together and put our records together with the Carras et al. 2009 record in Crassiformis. So one thing to take into account here is that once we're now just looking at the time slice between 2 and 5, but also that these are subsurface records of mixed species. So usually, because I've been talking about the same species and the same calibration, those temperatures, those relative temperatures are unchanged. But now we have a different species and a different calibration. So these relative temperatures, like the total amount of cooling, might not be a real result. It might just be an artifice of the calibrations that we used. But what is true is the relative changes, right? So we have this strong step-like cooling that was observed in the Crassiformis record in purple. And we see actually quite a bit of cooling in the East Pacific, but we don't see the same amount of cooling in the West Pacific here in blue or in the Northeast Indian Ocean. So that doesn't really suggest that the Indo-Pacific warm pool cooled in response to the Indonesian throughflow restriction, right? There's definitely other things that are making global climate cool that are not related to the Indo-Pacific warm pool and that are not related to the Indonesian throughflow. So, quick conclusions. The Indo-Pacific warm pool thermocline cools similarly in the Northeast Indian Ocean than in the West Pacific. We saw those records follow each other pretty contemporaneously throughout the 5 million year history. We didn't really see an evidence that the 2 meter is responding to a depth of habitat. It seems that the thermocline cooling is a true cooling signal. The West Pacific, the East Pacific, and the Northeast Indian Ocean have independent water sources. So those carbon isotope ratios are all on their own trend lines. They are not interacting with each other. That's expected. But we don't see a step-like cooling at the Indo-Pacific warm pool at either side of the throughflow that is suggesting a tectonic threshold, right? There's no point where you're suggesting, okay, now the Indonesian throughflow is small enough, and we're gonna switch our water sources. It's possible that the Mid-Pliocene tectonic-driven subsurface cooling, which is a mouthful, is limited to the southern part of the Indian Ocean. So the southern part of the Indian Ocean is cooling. We see those records. We're taking those records at face value. But that cooling that is happening in the southern part of the Indian Ocean is not being transferred to the northern part of the Indian Ocean. So it's hard to say, okay, we have a big global event where the Indo-Pacific wormhole, which is such a big part of global climate, remain unchanged because of it. And yeah, so the Indo-Pacific thermocline seems to cool as the climate cools. So it might be, and it is possible, that these signals are really disconnected, right? That you have this big system and these big thresholds that are moving all through the climate system, cooling the climate system, and that signal's coming back and then cooling the Indo-Pacific wormhole. I mean, that is possible, but it's definitely something we need more data on. It's definitely something we need to investigate more deeply, because it doesn't seem like that tectonic shift is creating a similar shift at either side of the Indo-Pacific wormhole. That is the end of the presentation. Yeah. Yeah.
You talked about the AMOC speeding up when it got warmer, but isn't there a conversation now that with warming that the AMOC could slow down?
Yeah. So let's actually spit it up through this quite fast, because I realized that my timer is not actually the timer of this talk. But, so we can actually take a little bit of time to slow down. So the idea of AMOC slowing down and cooling, right? So right now, AMOC is transferring heat signals from the tropics to the northern hemisphere, right? That's the big Gulf Stream that's happening here. And because this is where new deep water is being generated, you are sinking that water, right? And transferring the heat. If you slow down AMOC, it means that you have less sinking, and the warm temperatures in the tropic stay in the tropics. You don't have that warming tail that's coming into the northern hemisphere. It is basically, you know, the Gulf Stream is the reason why in Europe you can grow strawberries, and in Canada you have polar bears, right? Like at the same latitudes. That's a little bit of an exaggeration, but the Gulf Stream is transferring these really big heat signals, right? And that's part of why we talk about tropical heat transfer as such a big part of the equation, right? Whatever is happening at the tropics, like if the tropics are really warming and that temperature is being transferred to the system, then the northern hemisphere is gonna warm. But if the tropics are cooling, then that will also transfer to the system, right? Like the Indo-Pacific wormhole, well, in this case, the Indo-Pacific wormhole doesn't really have much to do here, except that the signal is still being connected. So yeah, that is a more complicated part of this conversation is really what's happening with the northward migration of the westerlies, which has been used in the past as a reason why deglaciation happened, or as a reason why deglaciation strengthened, like it's why carbon storage strengthened. So I think that it's hard to put a lot of records together, and you really do need, I mean, assuming that all records are true, right? Assuming that all of the records are recording something that actually happened, right? Like there's no like data falsification, there's no like, assuming all the records are true, there has to be one story to bring them all together, right? Like there has to be something that we can transfer to the global system. And if we can't find it, like if we can't do that, we don't have information to feed our models, right? Like, so we try to do it, like we try to chip at it slowly. Yeah.
You mentioned you want more data to try and figure more things out, but what does that mean? Does that mean like more cores around the world, or deeper cores, or anything else that you really want?
Yeah. So I actually have a core, like right here. And that is from the most recent cruise that Ivana went on, Expedition 363. And that record we're currently using to look at like more calibration-related questions about the changes of magnesium, calcium in seawater through time, which are not, didn't really bring it up in this talk because we were just looking at relative magnesium, calcium to magnesium, calcium proxies. But once you're trying to talk about other proxies, like organic proxies and also magnesium, calcium, now you really need to get, like, your temperature needs to be very solid, like, because you are comparing proxies. So that's what we're doing with that record. We're actually we did like a really high resolution glacial intervals, or glacial to interglacial intervals at a really, really high resolution. So we could measure magnesium, calcium, and do a magnesium calcium temperature estimate. And so that our collaborators in Norway could do clump isotope measurements and do a clump isotope temperature, and we could compare them. But what I want to do in that record next is to actually generate a long-term record like the one that we have here, and look at the subsurface temperatures. And because if anywhere it's going to show whether the Indo-Pacific subsurface cool will be that record. Like if that record here doesn't show any cooling, then the cooling that's observed over here must be coming from somewhere else. So yeah, that's like a really next step in this research, is to generate that record. Half the samples, they are being washed. I just need some time. Or volunteers. Either one will help. But yeah, that's a big step for future research. And in terms of my future research, to answer these questions. But there's a lot of things we don't know about these times. And these are relatively low resolution records. I mean, when you have a couple hundred samples for 5 million years. So generating a really high resolution record of these intervals where the Indo-Pacific, when the Indonesian throughflow is restricting, is also going to be very helpful, like actually targeting that time period in detail. Another thing is that we are looking at mostly Tumida records, and this is a cruciformis record. Tumida as a species is a little bit better understood. It is a record that it is a species that's been used quite a bit, whereas cruciformis is not. So there's some, and I don't know their carbon isotope record. So we kind of do like our work to make sure that the things that we're saying have like several other layers of information where we're not extrapolating too much. But yeah, just like, I think that will need to be, we will need to possibly do a pair species calibration. We probably have to at least attempt to look at the cruciformis in this sites and look at the Tumida, or maybe they can look at the Tumida in their site and we can see, like, is this just a species thing? The Tumida has been shown in other research to pretty much stay with the thermocline. Like whatever the thermocline is, Tumida seems to stay with it. In different parts of the world where you have thermocline at different depths, Tumida seems to be at the thermocline in every region. And I don't know if that's true of cruciformis. And also, yeah, another part of it is that the model was a 400-meter depth, and we don't really have a 400-meter depth species that we can look into. Like, that's not really an option.
Are there any proxies for where the IPCC was located?
I love talking about the IPCC. Yeah, okay, so having proxies of the IPCC is hard because it's wind, right? Like, wind doesn't really leave like a friend wind behind. Like, it just goes and then it's passed. So what a lot of people have been doing, including my PhD work, was looking at dust provenance, right? So the IPCC, well, the winds that are around the IPCC are carrying dust, and then the IPCC tends to be like a precipitation zone, right? So there's a big area of dust deposition. And if you can see changes in the source of dust that's deposited on either side of the ITCZ, that is one way of tracking the ITCZ position. That's what I did for my PhD in the Central Pacific. In order to do that work, for example, in the westerlies, it's about finding an area where you have records that are the dust, so that the lithogenic fraction is mostly coming through dust. So you need to be pretty confident that that's a dust signal. If you get too close to the polar front, you're going to have a lot of lithogenic material that is going to be iceberg deposited. So then that's like not great. Try to look at westerly changes. So that's more in the westerlies, not necessarily in the ITCZ. But yes, it's all about finding a place in the world where you can do the world, and you can sort of like chip away at all of these other possibilities, right? Like you want to just target. With the work that we did for the ITCZ for my PhD, we were in the middle of the Central Equatorial Pacific, the Line Islands. So the Line Islands is an underwater ridge, really. But we were in the middle of the Pacific, so we know, okay, if we have lithogenic material here, it's either coming from volcanism or it's coming from dust, right? There's no really other sources that are going to bring material to this place. And then the volcanic material tends to leach away really quickly. So we felt relatively confident that we could chemically separate the dust from the not dust. But even then, you end up with something that you call the operationally defined luminosity decay fraction. Because there's only so much you can like, there's only so much confidence you can have that when you have a stack of marine sediment, you can like take away the dust, you know, like, yeah. I like talking about the ITCC. And I also realized that I don't understand the ITCC at the same time. Whenever a physical oceanographer talks to me about it, I realize that we have very different definitions of what the ITCC is. I'm like, oh yeah, this like 10-degree range where I'm seeing like a little bit of a shift every 500 million years. Like, no, 500,000 years. But